Hello everyone, welcome to the course of ultrasonic testing technology. The main content of this course is the selection of ultrasonic testing equipment and probes. Through the study of this lesson, I hope to achieve the following teaching objectives. Master the selection principle of ultrasonic flow detector. Master the selection principle of ultrasonic probe. First of all, we will learn the selection principle of ultrasonic flow detector and mainly consider the following aspects. When conducting outdoor flow detection, the first consideration should be convenience of carrying. So the flow detector with light weight and a small volume should be selected. Secondly, as outdoor flow detection is more complex than indoor flow detection, with stronger electromagnetic interference signals and stronger light, it is appropriate to choose a flow detector with strong anti-interference ability and high screen brightness. When detecting thin parts of near-surface defects, a flow detector with a small bland area should be selected in order to effectively find defects. In order to effectively distinguish the adjacent defects in the sound beam propagation direction, and the flow detector with narrow pulse and good resolution should be selected. When testing large thickness specimens or high attenuation materials, considering the attenuation characteristics of ultrasonic propagation in the workpiece, it is advisable to select a flow detector with large emission power, large gain range and low electrical noise when testing such workpieces. In view of the high requirements for defect positioning, it is appropriate to select instruments with small horizontal linearity area and good horizontal linearity. In view of the high requirements of defect quantification, it is appropriate to select the ultrasonic flow detector with small vertical linear area and higher antenna accuracy, so as to obtain more accurate defect equivalent size. In addition to the above conditions, when selecting an ultrasonic flow detector, we should also consider the stability of the instrument's performance, the repeatability of the test results, the storage function, and the degree of intelligence and instrument, so that the instrument can improve the flow detection efficiency and reduce the work intensity of the inspectors while ensuring accurate detection. Probe selection. First, probe type selection. Common probe types can be divided into longitudinal wave straight probe, transverse wave oblique probe, surface wave probe, twin crystal probe, and focus probe. Among them, the longitudinal waves straight probe, also known as the flight probe, can transmit and receive longitudinal waves, has large detection depths, a wide range of applications, and a high detection sensitivity. It is most suitable for detecting defects parallel to the detecting surface. It is mainly used for ultrasonic flow detection of plates and forgings. The S-wave angle probe generates S-wave by refracting the P wave from the internal wafer through the plexiglass wedge. The detection depth is small, which can be used for the parts defect to be detected by the straight probe, and the detection sensitivity is high. It is mainly used for defect detection at a certain angle with the detection surface. The surface wave probe can transmit and receive surface waves. Its shape is similar to that of the shear wave and probe, except that the incidental angle of the shear wave angle probe is between the first critical angle and the second critical angle, and the incident angle of the surface wave probe is larger than the second critical angle, thus generating surface waves propagating along the workpiece surface. So it is suitable for detecting surface and near-surface defects of the workpiece, such as surface cracks and pores. Double crystal probe, also known as split probe, is actually a combination of two single probes, one for transmitting signals and the other for receiving signals. There is a sound energy concentration area near the bottom of the double crystal probe. With this feature, it can detect near-surface defects and improve the detection sensitivity in the detection area. The focusing probe can focus the ultrasonic waves into linear or point shapes and concentrate the acoustic energy at the focal point, which can improve the flow detection sensitivity and resolution. There are two methods to realize ultrasonic focusing by focusing probe. One is to make piezoelectric wafer into concave spherical surface and directly focus the emitted acoustic wave, which is called self-focusing probe. The other is composed of a straight probe and an acoustic lens. The role of the acoustic lens is to achieve beam focusing, which is called a lens focusing probe. The ultrasonic volatility from the focused probe has good directionality and concentrated energy, which makes this type of probe have the characteristics of high detection sensitivity, narrow sound beam, high lateral resolution, and high positioning accuracy. It is commonly used to detect plates and detect curled parts in the operation with liquid immersion method. To sum up, the selection of a probe type generally needs to consider the shape of the workpiece, the location and the direction of possible defects, and we should try to make the axis of ultrasonic beam perpendicular to the defects. In this way, stronger defect reflection, sound pressure, and higher defect deflection rate can be obtained. The selection of probe frequency and ultrasonic probe frequency has a great impact on the detection results. Generally speaking, the selection principles of probe frequency are as follows. For workpieces with small defect size, fine grain and small thickness, higher frequency should be selected. For large thickness workpiece, coarse grain and high attenuation material, lower frequency should be selected. The frequency of industrial and commercial ultrasonic probes on the market is generally between 1.5 to 15 MHz, with a wide selection range. In pulse reflection ultrasonic testing, the following factors should be considered in the selection of ultrasonic probe frequency. The sensitivity of ultrasonic flow detection is about half wavelength due to diffraction of ultrasonic wave. The shorter the wavelength, the better to find smaller defects. The probe has high frequency, small pulse width, and better resolution, which is conducive to distinguishing adjacent defects in the flow detection direction. According to the propagation characteristics of ultrasonic wave in the medium, if the frequency is high and the wavelength is long, the half diffusion angle is small and the directivity of the acoustic beam is good. The higher the frequency, the longer the near-field region, which is unfavorable to flow detection. The attenuation of ultrasonic wave increases sharply with the increase of ultrasonic wave frequency and medium grain size. Therefore, when selecting the frequency of ultrasonic probe, it is necessary to comprehensively analyze and consider various factors and reasonably select the detection frequency. Generally, under the condition of ensuring the detection sensitivity, the frequency should be as low as possible to reduce the acoustic energy loss. Selection of probe wafer size. The shape of commonly used ultrasonic probe wafers is generally round and square. The wafer size of the probes has a certain impact on the ultrasonic flow detection results. The following factors should be considered when selecting: the increase of the wafer size, the decrease of the half diffusion angle, the good directivity of the acoustic beam, and the concentration of the ultrasonic energy are beneficial to the flow detection. With the increase of wafer size, the length of near-field region increases, which is unfavorable to flow dictation. The larger the wafer size, the stronger the ultrasonic radiation energy, the wider the scanning range of the probe's non-diffusion area, and the ability to find the long-distance defects is enhanced. Therefore, for workpieces with large flow dictation area, in order to improve the flow dictation efficiency, larger wafer probes should be selected. When detecting thick and large workpieces, in order to obtain enough ultrasonic radiation energy to effectively detect long-distance defects, large wafer probes should also be selected. For small workpieces, in order to improve the positioning and quantitative accuracy of defects, it is more suitable to select small wafer probes. For the workpiece with uneven surface and large curvature, in order to reduce coupling loss, the small wafer probes should also be selected. The choice of incidental angle, the ultrasonic testing, the axis of ultrasonic beam should be perpendicular to the defect as much as possible. Therefore, the choice of incident angle should be determined according to the type and location of possible defects in the test object and the structure of the workpiece itself. Taking the transverse wave angle probe detection as an example, the refraction angle has a great influence on the deflection sensitivity, the direction of the acoustic beam axis, and the sound path of the primary wave. When the plexiglass transverse wave, the angle probe is used to detect the steel workpiece. Third, when it is about 40 degrees, the sound pressure reciprocating transmit reaches the highest. That is, the dictation sensitivity reaches the highest. It can be seen that the larger the value of K, delta, the larger the angle, the greater the sound path of the primary wave, as we can see in these phrases. In actual detection, when the workpiece thickness is small, the large K value should be selected to increase the sound path of the primary wave and avoid dictation in the near field area. When the thickness of the workpiece is large, the smaller K value should be selected to reduce the attenuation caused by the excessive sound path, so as to find the defects at the deeper part. Okay, that's all for this class. See you next time.